We're very happy to have Aleksander Doan speaking in our seminar today on equivariant transversality meets geometric measure theory.
Thank you for the invitation. And I changed the title of the talk last minute because really what I want to stress in this talk is this, maybe this meets word here. So I won't really say anything new about equivariant transversality, and I won't say anything new about geometric measure theory, but somehow I want to advertise the idea that you can combine the ideas from both fields to say something about symplectic manifolds. And everything I'm going to talk about is joint work with Thomas Walpuski, and the last part of the talk is also joint work with Eleni Ionel, who gave a seminar talk at this seminar 2 weeks ago. Let me begin with some motivation. So this is an old problem in algebraic geometry, studied in the 19th century by Italian school of algebraic geometry, Grassmann, Schubert, and people like that. Take a complex projective manifold X, and how many holomorphic curves are there in that manifold? Perhaps you want to fix genus or a homology class that these curves represent, or maybe you want to require that these holomorphic curves pass through, say, certain constraints, so points or other submanifolds. And this is the subject of enumerative geometry. And here are some famous examples. In CPN, 2 points determine a line, meaning a genus 0 curve of degree 1. And there are 27 such lines contained in a cubic surface, and famous number, 2,875 lines contained in a quintic 3-fold. And that's the starting point of mirror symmetry and so on. So there are many results in algebraic geometry of this sort. So a little bit more systematically, if we want to study this problem, we would say, fix a genus G and a homology class in my manifold, A, and then look at the moduli space of curves of this genus G and a homology class A. And it is not always a manifold, but if it is a manifold, it has a dimension given by this formula. So this formula involves a genus and a homology class and also the first class of X. So we call it the virtual dimension or expected dimension. So if this virtual dimension is 0, we can hope that the moduli space is just a collection of points, and then we could count them, and maybe that gives us an invariant of our complex manifold. And of course, if the dimension is greater than 0, you can reduce the dimension to 0, but by imposing certain constraints. So for example, require that these curves pass through certain points. But in this talk, I will always consider the 0-dimensional case. So anytime I talk about the holomorphic curve, I will always assume that this curve lies in a moduli space of virtual dimension 0 for the rest of the talk. And here is an important case. The main case of interest, if the dimension of your manifold, real dimension, is 6, then something interesting happens that in this formula, the virtual dimension does not depend on the genus of the curve. It only depends on the homology class. So all curves, so for example, if you have a homology class such that the C1, the first class, pairs to 0 with this homology class, then the virtual dimension of the moduli space of curves in that homology class is 0 for any genus. And that's something special for dimension 6. And homology classes which satisfy this condition we call Calabi-Yau classes. So of course, if C1 of X is identically 0, if you are as Calabi-Yau manifold, then all homology classes satisfy this condition. So even though the problem is inspired by algebraic geometry, we can leave the realm of algebraic geometry and consider more generally symplectic manifolds. So take a symplectic manifold and equip it with an almost complex structure, which is tamed by the symplectic form. And the main question that, the main motivation for this talk is the following question. other symplectic invariants which count embedded J-holomorphic curves in X for a generic choice of the almost complex structure. So what I mean by that, you want to count these curves and then you want the result to be independent of the choice of J, which is some sort of auxiliary data. And of course, this is a question many people thought about. So for a general symplectic manifold, there is really no reason for the count of embedded J-holomorphic curves to be independent of this choice of an almost complex structure. In fact, even it's not even necessarily true that if you choose a generic almost complex structure J, then there will be finitely many curves of given genus or homology class, even if I'm always assuming here virtual dimension 0. Right, so even to define the count of curves is a non-trivial task. And the point is that the moduli space of embedded curves is not compact because the embedded curves can degenerate either to singular curves or to multiple covers of other embedded curves. So, but really what I want to stress is this point. Right, so if you want to answer this question, whether you can count embedded curves, you have to do something, right? You either have to restrict the class of manifolds, symplectic manifolds you're interested in, or you have to change the meaning of counting curves, of what you mean by counting curves. So you have to give up on something. And there are many successful theories who do that. So perhaps the most familiar one is the Gromov-Witten theory, in which you relax the notion of a J-holomorphic curve, and instead you look at parametrizations of such curves, so pseudo-holomorphic maps. And this is an invariant which in some sense counts such maps, and it's defined for a symplectic manifold of any dimension. Perhaps more in the spirit of this question about embedded curves that I asked, in dimension 4, Taubes define an invariant which counts embedded curves with certain integer weights. So really curves and not maps, but that's only defined in dimension 4. And moreover, Taubes showed that this invariant is equal to the Seiberg-Witten invariant defined using gauge theory. And in algebraic geometry, we have a different family of invariants, which are broadly known as Donaldson-Thomas invariants, which instead of maps count sheaves or equivalently subschemes of complex dimension 1. And these invariants are defined only in dimension 6 and 8, and also only for projective manifolds. So they are defined using methods of sheaf theory, which are not really available in symplectic geometry. But interestingly, there is a conjecture which says that these invariants are equivalent, not equal, but equivalent to Gromov-Witten invariants. So conjecturally, they would be invariant under symplectomorphisms, even if they're only defined using, if they're defined using complex structure, in the end, they should be independent of the complex structure and dependent only on the symplectic structure. So this brings us to an interesting question. Can we find definition of Donaldson-Thomas invariants in symplectic geometry without using the theory of coherent sheaves? And you might be surprised when I say, I started my talk with a question of counting embedded curves, and then I say, well, there's this theory counting subschemes. And of course, subschemes are much more singular than, say, images of pseudo-holomorphic. They're very singular objects. So you could argue that, well, that's not really in the spirit of my question because you just replaced curves by very singular objects. But in some sense, these subschemes are in the category of algebraic geometry, they are embedded objects, right? So, I mean, they can have multiplicities and so on, but you really think of them as something sitting inside in your manifold and not being parametrized by a map. And if you imagine that there is some symplectic definition of Donaldson-Thomas invariants, then in the end, you could always take a generic J for which all J-holomorphic curves would be embedded. So you could imagine that these subschemes are really supported on embedded curves. So even though they're very singular, somehow they are in the spirit of counting embedded objects. And I'll get back to this point later. So let me say something about Gromov-Witten theory and what are some issues with it. So very briefly, Gromov-Witten theory studies J-holomorphic maps. So these are maps from Riemann surfaces, which are J-linear, whose derivative is J-linear. So here, small j is the complex structure on the Riemann surface, and big J is our almost complex structure on X. And you form the moduli space of such maps with fixed genus and fixed homology. And there is a Gromov compactification, which is obtained by allowing the domains of maps to degenerate to nodal Riemann surfaces. And there is also a stability condition that will impose on such maps. And now the Gromov compactness theorem says that if you look at this bigger moduli space consisting of maps from nodal surfaces, then this is a compact space. So you can use this compact space to define the Gromov-Witten invariant. Again, we are interested in the case that when the virtual dimension is 0, so you don't need to put any insertions, and the Gromov-Witten invariant is independent of J, and it's a rational number. So you can ask, what does this rational number actually count? Well, it has contributions from all sorts of maps, including maps that are not embeddings. And that's why it's a rational number, because you, in some sense, divide by the rank of the automorphism group. Each curve contributes a rational number because it has automorphisms. So if you are interested in the problem of counting embedded curves, you see that there are two issues with Gromov-Witten theory. The first one I already said, that maps in this Gromov moduli space are not necessarily embeddings. So a typical example is that you can have a map whose image, say, is an embedded curve, but your map is a multiple cover of that. And another example is that you could have, let's say, an embedded sphere in your manifold, but then you consider nodals, because you allow nodal Riemann surfaces. So you, for example, take something like that and send the higher genus component to a point. So, so that shows that a single embedded J-holomorphic curve of genus 0 will have contributions. A priori, can have contributions to Gromov-Witten invariants of arbitrary genus. So of course, this is not, if you're interested in geometric, in counting geometric curves, there's some redundancy. And then there is the second problem, that Gromov-Witten theory deals only maps of fixed genus. So maybe this is a less obvious issue, because in the end I said, well, you can always fix genus. But in some sense, this is weird that Gromov-Witten theory doesn't tell you anything about what happens when the genus becomes large, right? So for example, Gromov-Witten theory does not exclude the possibility that you have a sequence of curves of higher and higher genus, and in some sense they concentrate to a curve, to some other curve. So, you can have higher and higher genus, and maybe in some sense they collapse to a curve of origins, which is very weird and probably doesn't happen. But using methods of Gromov-Witten theory, there is no way of excluding such weird behavior. And also, if you are interested in the problem of finding a symplectic analog of Donaldson-Thomas theory, then you quickly realize that it has to be something very different from Gromov-Witten theory, because in Donaldson-Thomas theory, I said you count these subschemes and you only distinguish them based on their homology class. You don't prescribe the genus of your curve. So if you want to get closer to the problem of finding a symplectic analog of Donaldson-Thomas invariants, then you have to go beyond Gromov-Witten theory. You have to have a framework which allows you to treat curves of all genus at the same footing. So this is the motivation for what I'm going to talk about. So we want to find something that goes beyond Gromov-Witten theory. Maybe imitating Taub's work in dimension 4, maybe we can find some invariant of symplectic manifolds, which in some sense is a count of embedded curves with weights. So the main theorem I'm going to state does not define such an invariant, unfortunately, but you can think of it as the first step in this program, that if you want to define an invariant which is a count of embedded curves with weights, then the first step you should do is to show that for a generic J, there will be finally many of such curves. And this is what this theorem says. This is a joint work with Thomas Walpuski. And it says that if X is a compact symplectic six-manifold, then for a generic tamed almost complex structure J, there are finally many embedded J-holomorphic curves in every homology class which satisfies this condition for virtual dimension being 0. And this condition is not very restrictive. So if this number is negative, then generically there are no curves, so that's uninteresting. If it's positive, then you can prove the same result when you impose certain insertions, constraints on your curves to reduce the dimension to 0. So there is a straightforward generalization to arbitrary homology classes. In some sense, this case is the most interesting one. So are there any questions about the statement of the theorem? If not, let me make 2 remarks. So the first remark is that in this theorem, we don't specify genus. We don't say there are finally many curves for each genus. We say there are finally many curves for each homology class. So allowing arbitrary genus. As a result, this theorem cannot be proved using Gromov's compactness theorem, which deals only with maps from Riemann surfaces of fixed genus. And then you can ask a question, okay, so I have these finally many curves, maybe I can simply count them with signs, and this is an invariant of my symplectic six-manifold. And typically it isn't, but there's a theorem of Singer that if A is a primitive class, and by primitive, I mean that A is not of the form K times B, for some B, which is also an integer homology class. Then the signed count of such curves is in fact a symplectic invariant. So in this special situation, you can simply naively count embedded curves as a symplectic invariant. And there is an alternative proof of this result with Walpuski, based on studying bifurcations of such curves. Because Singer's proof uses the fact that Gromov-Witten invariants are invariants. But you can also ask directly, okay, maybe I can directly show that if I deform J, the number doesn't change, and that's what we do. And the third remark is that even though maybe I started this talk by dismissing Gromov-Witten theory unjustly and saying, oh, it doesn't count embedded curve, in the end, one of the sources of motivation for this result is that it does tell us something of the structure of the Gromov-Witten invariants. So this is related to the Gopa-Kumar-Vacha conjecture. And I will not talk so much about this because that was the subject of Eleni Ionel's talk from 2 weeks ago, but I will have one slide about this later. So for most of the remaining part of the talk, I want to say something about what goes into the proof of this result. So using basic transversality results for simple J-holomorphic maps, you can show that for a generic J, the moduli space of curves is discrete. And again, when I say curves, I always mean in the stock curves lying in zero-dimensional moduli spaces. And because we are in dimension 6, you can always guarantee that these curves are embedded and pairwise disjoint, simply because 2 manifolds embedding into 6 manifolds will have pairwise disjoint images. So if we want to prove that the number of these curves for fixed homology class is finite, we have to show that this moduli space of curves for fixed homology class is compact. And this is fixed homology class any genus. So as I mentioned, because we want to treat curves of all genus in the same way, we cannot use Gromov's compactness theorem. We have to replace it by something else. And geometric measure theory will provide us tools for studying sequences of J-holomorphic curves of varying genus. So the first step of the proof is using geometric measure to find a way of detecting when a sequence of embedded curves can degenerate. And once we do that, then we'll use Chris Wendl's equivariant transversality result to say, well, this thing that you just described cannot happen generically. So in some sense, the proof has 2 steps, and each step uses different tools. So let me begin with the first part. So the proof will be by contradiction. So we want to show that for a fixed homology class, there are finitely many curves, embedded curves. So choose this generic J such that the moduli spaces are discrete, and suppose by contradiction that there is an infinite sequence of curves with the same homology class. So I want to think of these curves as currents. So a 2 current is a linear map on the space of 2 forms, and every curve defines such a current simply by integrating 2 forms over C. And there is a notion of a mass of a current. And in this case, the mass is simply the area of the curve, which maybe I should put, which will be in this case, it's the topological invariant. It's the pairing of the homology class of the symplectic form with the homology class of the curve. So in particular, if we have curves all in the same homology class, then we see that the sequence of currents has bounded mass. So it's bounded by some M. And then there is a compactness theorem in geometric measure theory called the Federer-Fleming compactness theorem, which says that if you have sequence of integer rectifiable currents of bounded mass, then you can pass to a limit, and the limit is also an integer rectifiable current. So just passing to a limit as a current is too weak, because currents can be some very crazy functionals on the space of 2 forms. But there is this notion of a good current, the one which is integer rectifiable, and the Federer-Fleming theorem says that this space of integer rectifiable currents of bounded mass is compact. So you can think of it that these are currents given by integrating over countably many submanifolds, which can possibly intersect in a very complicated way. But still, they are much better than just a generic current, which is just a function on the space of 2 forms. So in any case, we get this limiting current. And the integer rectifiable currents have a tangent space at almost every point. And because our curves were pseudo-holomorphic, this tangent space will be also invariant under the action of J. So it's some sort of singular, you can think of it as a singular pseudo-holomorphic object. But now there is work of Telelis, Spadar, and Spalor on regularity of semi-calibrated currents, which says that if you have such an integer rectifiable current whose tangent space is preserved by J, then in fact it is a linear combination of singular pseudo-holomorphic curves. So it's even better than just a general integer rectifiable current. It's in fact as good as you can hope for. So this limiting current, and I should mention that this result, this earlier result of Tian and Riviere, and in dimension 4, this was also proved by Taubes. So there's a long history of results of this sort. It's a regularity. It's a regularity theorem. So the upshot is that after we pass to the limit, the limiting current is a linear combination with integer weights of the currents which are simply given by integration of two forms over possibly singular pseudo-holomorphic curves. But now there is an index calculation which shows, because we started with curves that had index 0, and because our J is generic, in fact, we can show that all these curves will have index 0. Each of the components will have index 0. And moreover, since they have disjoint images, and the support of this current must be connected, it follows that there must be only one component. Because if there were two, right? So C1 and C2, this current will have disconnected support, but it's a limit of currents with connected support. So with some sort of index argument, you can show that because our J is generic, in fact, this current is a single curve, is a current associated with a single curve, which must be embedded, multiplied by an integer. So in fact, what happens is that Cn converges to M times C as currents. So this is the collapse of a sequence to a multiple curve. So we want to further analyze this collapse. How can it happen that we have a sequence of curves which converges as currents to M times C? So here is an idea of Taubes. Since we assume that J is generic, this limiting curve C is smooth. So it has a normal bundle, N. So you can think of it that we have this sequence Cn, which gets closer and closer to the 0 section in the normal bundle. So what you can do, you can now rescale the normal bundle in the normal direction such that each of these curves, call them C and twiddle, has now distance, Hausser distance 1 to C. So the original sequence collapsed to the 0 section, and so I can start rescaling the normal bundle to prevent the sequence from collapsing. So for example, I can fix the Hausser distance of the rescaled sequence to be 1 to the 0 section. So now I get a new sequence of curves called C and twiddle. And I can repeat my argument. You can show that they have also bounded mass, and therefore you can also extract a limit as currents. And you can also apply regularity theorem to show that this rescaled sequence converges to some pseudo-holomorphic curve, possibly with multiplicity, contained in the normal bundle. So after repeating this entire argument, you get some new curve, C twiddle, which is now in the normal bundle. And by construction, it's at Hausser distance 1 from the 0 section. So in particular, it's not equal to C. So maybe I should erase something because it got busy. So after rescaling, this is the situation that you have C here, and you have some kind of curve here, C12. And this is all happening in the normal bundle. So now what you can do, you can intersect the C twiddle with each normal fiber. And you can show, so maybe it has multiple intersections. And you can show that this defines a multi-valued section of the normal bundle. So the section associates to this point in C, the points lying in the fiber, the intersection of the fiber with C twiddle. So you can think of this section as the section of some symmetric power of the normal bundle. Or equivalently, such a section will be determined by a choice of an orbifold structure on C, a choice of an orbifold local system, and a section of the normal bundle twisted by this orbifold local system. With the local system, essentially remembers how the branches change. And it has to be an orbifold local system because some branches can collapse. So that you encode in the orbifold structure. So the upshot is that we started with a sequence of curves in the end, and we found that when the collapse happens, such a collapse leads to a multi-valued section of the normal bundle. And this section is not some random section, but because the curves we started with are pseudo-holomorphic, there should be an elliptic equation for our section. So this is what this point says, that because our curves were pseudo-holomorphic, after we start rescaling, the limiting curve will be pseudo-holomorphic to some rescaled almost complex structure in the normal bundle. And the condition for C twiddle being pseudo-holomorphic with respect to that almost complex structure is an elliptic equation for this section, this multi-valued section. So the situation is this, that we have C, we have the normal bundle, we twist it by some orbifold local system, and the C twiddle can be thought of as a graph locally, this section is just K sections of the normal bundle. So that gives us taking the graph of that, we get this curve C twiddle. And this section satisfies the equation D of S equal to 0, where D is a Cauchy-Riemann operator on the normal bundle twisted by this local system. On the normal bundle, we always have the usual deformation operator, which controls the normal deformations of our curve. And we can always twist such an operator by a local system. So we get an elliptic operator, and we get a section which is a solution of this elliptic equation. Are there any questions about this construction?
So where did we use the fact the dimension was 4?
Oh, we didn't use the dimension is 6.
Sorry.
So let me scroll up here. The dimension is 6. But that's a good question. So we used it because in the step that actually I didn't write down. So when you do this rescaling, sorry, I keep scrolling so much. So when you do this rescaling, you get that the limit is a combination of curves. But in general, these curves, even if you started with a curve of index 0, these curves could have any index. But in dimension 6, the index is because there is no term involving the genus, the index depends linearly on the homology class. So you can conclude from this that if the original curve had index 0, then all of these components will have index 0. And then you can conclude that there is only one component.
I see.
I didn't write the formula, but it's this kind of numerology for the index formula.
Can I ask a quick question?
Yep.
So like in higher dimensions, for example, you could have a family of curves degenerate to something which then has like a bigger index. And then when you compute this normal operator, even though its index is negative, you look at the sum of these, then that's index 0. And so you could expect these things to still exist. Is that kind of the...
Well, that could happen, but here if there are multiple components, then we fail at the next step, because it could be that it will be something like that, right? So because curves of higher index can intersect with each other and will intersect with each other. So I cannot, if I have something like that, then I won't be able to take the normal bundle and do this rescaling argument. So I really want to have a single curve, and which is embedded and possibly with some multiplicity. Because if it's a union of curves, I cannot do this normal bundle argument.
Okay, thank you.
Okay, so the upshot is we started with the sequence, and we discovered that if a sequence of embedded curves collapses as currents, then that leads to a pseudo-holomorphic section, multi-valued section of the normal bundle. So a solution to the Cauchy-Riemann equation, which is multi-valued. And now you can check using, for example, Orbifold-Riemann-Roch theorem, that the index of such a twisted operator in our case will be non-positive. So if everything was generic, we would expect that this operator has no kernel. And if this operator has no kernel, then we arrived at a contradiction, because we just found something in the kernel. And we know for sure that this S is non-zero, because our rescaling procedure was made in such a way that C twiddle was not equal to C. C twiddle was in Hausdorff distance 1 from C, and it's a graph of S, so in particular, S cannot be a zero section. So if we could show that for a generic J, this operator has no kernel for every embedded curve, then we are done. And we expect that it will have no kernel because its index is non-positive. So that would be the end of the proof. But there is a very serious difficulty here. This operator, by construction, is an equivariant operator, right? So we have the local system, and this D acts on the normal bundle, on the sections of the normal bundle twisted by a local system. So in its construction, it has built in the equivariance with respect to the to a finite group. So alternatively, the way you can think of it, that this is the deformation of that this local system defines a multiple cover of C, and this is the normal operator of the multiply covered curve. So it is equivariant with respect to the group of deck transformations of that multiple cover. So famously, symmetry and transversality are not compatible, right? So if you have such an equivalent operator, then you cannot apply the usual transversality arguments to show that for a generic J, the kernel will be, it will have no kernel. So this leads to a general question. Let's start with the Cauchy-Riemann operator L on a Riemann surface. Can we always perturb it in such a way that if you twist it by any local system, V, this operator L tensor V has the kernel and co-kernel of expected dimension? So this notation is a bit imprecise because I'm twisting an operator by a local system, but that just means that if I twist my bundle by a local system, locally I can write it as k copies of this operator, and that defines a globally defined operator for sections of the bundle twisted by the local system. So this is a hard problem, and this problem was solved by Chris Wendl, and it is the content of his super-rigidity theorem that you can always do that. So in our case, what the super-rigidity theorem says that for a generic J, you can always guarantee that this operator has trivial kernel. And since Chris Wendl gave a talk about this a while ago, I will not say so much about the proof of this theorem. But let me just make 2 remarks. By the way, I should say that this is the end of the proof, right? So once we have that this operator has no kernel, we arrive at the contradiction. So because we show that if we have an infinite sequence of curves which degenerate, that gives rise to a solution of to something in the kernel of this operator, and that's impossible. So are there any questions about the statement of the theorem or its proof? So if not, let me make 2 remarks about this super-rigidity theorem. So the first remark is that there is a technical step. Actually, the most technical part of this theorem, the super-rigidity theorem, is showing that I'm being a bit imprecise, but generally, there cannot be any algebraic relations between sections in the kernel of this operator and the kernel of the adjoint operator. So a very simple example of that, and these algebraic relations, in fact, they cannot hold at any point. So a very special example of that is the unique continuation theorem. If you have a section in the kernel of an elliptic operator, it cannot be that this section vanishes with all derivatives at the point. If such a section vanishes with all derivatives at the point, then in fact the entire section must be 0. So there is a generalized version of that, and that's the main part of the super-rigidity theorem. And this condition is somewhat similar to something called the surjectivity of something called the Petri map in algebraic geometry. So in algebraic geometry, we're interested in the Brill-Netter loci of divisors which have too many sections on the Riemann surface, and you want to have an estimate for the dimension of the locus of such divisors, and then there is a condition for the so-called Petri map, which guarantees that these Brill-Netter loci are of the right dimension. And the second remark I want to make is that this theory that Chris Wendl developed can be generalized to arbitrary elliptic operators twisted by local systems. And this is a joint project with Thomas Walpuski. So that gives us a general framework for proving a similar equivariant transversality results for in other contexts. So anytime you have some natural family of elliptic operators and you want to twist them by local systems, and you want to say that these twisted operators have kernels and co-kernels of the right dimensions, then you can run this machinery. But it will not give you equivariant transversality for free, because you will always have to prove that this first part holds, that you will always have to show that generally there can't be any algebraic relations between solutions. And that's usually a hard problem to solve. So Chris Wendl did it for Cauchy-Riemann operators. It's already a difficult proof. And you can see why that would be difficult, because in the end, in these equivariant transversality results, we want to say that something doesn't happen generically, right? And then I said, well, the main part of proving that is showing that something else doesn't happen generically. So it seems like we're translating one problem of transversality to another problem of transversality. But so the main idea that Chris used was that he translates this problem, the second problem, this so-called Petri condition, to a finite dimensional transversality problem, which then you can solve. Okay, so this completes the discussion of the proof of the theorem. So in the remaining part of the talk, I want to say how it is related to the idea of defining invariants of symplectic manifolds by counting embedded curves. So let me start with a digression on the Gopak-Marvafa invariants. So there is this conjecture that if you give me a symplectic six manifold, you can take all of its Gromov-Witten invariants and encode them in a big power series, formal power series. And then that there is a formula relating this generating function of Gromov-Witten theory to some other series, which has the property that it can be expressed using integer invariants. Right, so I said that Gromov-Witten invariants are rational because you count curves and divide the count by the number of automorphisms. And the Gopak-Marvafa conjecture predicts that these invariants can be expressed by integer invariants, so-called BPS invariants. And moreover, the second part of the conjecture says that only if you fix a homology class, only finitely many of these invariants are non-zero. So like Gromov-Witten invariants, these BPS invariants are parameterized by a homology class and a genus. And the second part of the conjecture says that for large genus, they vanish. So this is interesting if you remember what I said at the beginning of the talk, that you could start with let's say that our X has a single embedded J-holomorphic. So again, we are talking about six manifolds. So let's say that it has a single embedded J-holomorphic sphere and no other J-holomorphic curves. This sphere will contribute to Gromov-Witten invariants of any genus because you will have maps like this. So this is a somewhat weird feature of Gromov-Witten theory, that a single curve of genus 0 will contribute to Gromov-Witten invariants of any genus. So what this Gopak-Marvafa conjecture says is that the BPS invariants should not have this property. They should have a property that for high genus, the invariant is 0. And part A of this conjecture was proved by Ion and Parker. And this finiteness part was proved recently by Eleni Ionel, Thomas Walpuski, and myself. And I will not say anything about the proof because Eleni talked about this a while ago. And so I want to focus on something else. And let me just say that it's not only that these BPS invariants vanish for high genus. In fact, we get the structure theorem for these BPS invariants. Oh, by the way, I didn't say how, let me go back. I didn't say how they are defined, but they are essentially defined in terms of Gromov-Witten invariants by this universal formula. You express the Gromov-Witten series as by some universal transformation in terms of some other numbers, and you call those BPS invariants. So there is no geometric definition of the BPS invariant. So what I want to mention is that I stated this main result, that for a generic J, there are finitely many embedded curves in every homology class. And again, I'm talking about index 0 curves. And you can combine this main result with our work with Ionel to show a little bit more, to show that these BPS invariants have the following structure. It's a big sum. So you take a homology class and you look at all integers k which divide this class. So that's the first sum. Now the second sum is over all J-holomorphic curves which are embedded and represent the class A over k. And this is a fine, so these are finite sums. And this is by the main theorem. And then you count each of these curves with a certain weight. So weight depends on the genus and depends on the almost complex structure you chose. And even though this sum looks infinite, because we are summing over all integers, in fact, only finitely many of these will be non-zero. So this result doesn't tell us what exactly we're supposed to be counting here, but it does tell us that BPS can, for a generic J, you can express the BPS invariance as some sort of count of embedded curves in different homology classes with integer weights. And of course, here we don't define these weights. We just say, well, this is the, you can say that there exists something like a BPS contribution, and then you just say this is the BPS contribution. But it will be interesting to find what exactly is, if there is a geometric construction of these integer weights in a similar way, for example, to what Taubes did in dimension 4. And there is some progress in this direction by Shayun Bai and Mohan Swaminathan. So they are thinking about how to define geometrically these weights, BPS. So the upshot is that this formula tells you that there is some invariant counting embedded curves with weights, but it may be the way we have it now, it's maybe not very explicit. So that brings me to the last part of the talk, which is more speculative. So can we construct some invariant counting embedded curves where the weights themselves have some geometric meaning? Maybe not necessarily BPS invariants, maybe some other invariants. And this is joint work in progress with Thomas Walpuski. So the starting point is the following observation. Have a look at this formula that I just wrote above. So I'll scroll up again. So this formula has many sums, but the sum corresponding to k equal to 1, so when you just look at curves representing homology class A, you can show that this first order contribution is simply the naive count of curves. So you can show that the first order contribution to the BPS invariant is given simply by looking at all curves in that homology class and counting them with signs. So that's what I call a naive count of curves. And this is not an invariant, unless A is a primitive class. So the way you can think of this formula for the BPS invariant is that it's a naive, is the first order count is the naive count, and then you correct it by adding some correction terms. So can we actually guess a way of finding such correction terms which make the naive count an invariant? And the idea is to use gauge theory to construct such weights. And I will explain this idea. And moreover, we conjecture that such a construction would lead to a symplectic version of an invariant known in algebraic geometry. So I started my talk by saying that there are Donaldson-Thomas invariants in algebraic geometry, which count subschemes, and that it will be interesting to find a symplectic definition. And we conjecture that the symplectic analog will be given by the procedure I will now describe. So the minor technicality is that what I will talk about now is the Pandare-Pande-Thomas invariant, which is a version, it's a technical variant of the Donaldson-Thomas invariant. So I said that if the homology class is primitive, the naive count of curves is an invariant. So let's start with the next step and consider homology classes which are of the form 2 times B, where B is a primitive class. So the point is that the naive count of curves is not an invariant, because in this situation we can have a sequence of embedded curves in the homology class A, which converges as currents to 2 times C, where C is a curve in homology class B. And when this happens, the naive count of curves changes. And that's why it's not an invariant. So we can ask a question, can we correct this naive count by counting also curves in the homology class B, possibly with some weight? So the general form of an invariant that we look for is this. First, we sum all embedded curves in homology class A, maybe with some weight. Maybe this weight is just simply plus minus 1, just the usual naive count. But then we want to add a count of curves in homology class B, which is A divided by 2. And this count should really depend on J. And how should it depend on J? In the following way. Suppose that you have a family of J's, and as you vary J, a sequence of curves in homology class A converges as currents to 2 times a curve in a homology class B. And then it disappears from the moduli space. So the picture is a little bit like that. That if this is a picture of the, so if this is a picture of the moduli space of curves C twiddle in a homology class A, then at some point, maybe t equal 1/2. So this was t equal to 0. This is t equal to 1. And before the collapse, I had one curve in the homology class C twiddle. Then it collapses, it doesn't exist anymore. And then I don't have any curves in the homology class A. So if we want this number to be invariant under such changes, then we should require that this formula holds, that this is the amount that I lost in this transition. So it should be compensated by the jump in this weight W2 associated with the curve to which I collapsed. So how do you find weights which behave in this way? So the important observation is that such a degeneration happens, as in the proof that I discussed earlier. Such a degeneration happens when there exists this multi-valued section of the normal bundle. So that so if this degeneration happens, this C, let's say it's an embedded curve, so here's a normal bundle, it must admit a multi-valued section, in this case, 2-valued section of the normal bundle, which we know is a non-generic phenomenon. So we want to define a weight W2C, which depends on J, with the property that when J is a special, almost complex structure for which I do have such a multi-valued section, then this weight jumps. And well, let me just say very briefly that a similar problem was studied in other contexts in higher dimensional geometry. So let me skip that slide. And essentially the idea is that you can define such weights by counting solutions to a certain gauge-theoretic equation on the curve C. So I wrote down these equations here, but the particular form is not very important. The point is that on C, I will write down some equations with operators depending on J, and then I will count solutions to these equations. And I want the number of solutions to these equations to change when J is such that I have a multi-valued section of the normal bundle. So again, it's not very important at this point what these equations are, but the only thing I want to point out is that these equations involve certain connections and sections and so on, but importantly, they involve a section of the normal bundle twisted by an endomorphism bundle of some other. The normal bundle twisted by endomorphism of some other bundle. So locally, how you should think of it is a normal bundle tensor space of matrices. So now you could ask, well, why would that be that the number of solutions to this equation changes when I have a multi-valued section of the normal bundle? And again, I will skip probably this slide, but let me just say that this is the if you are familiar with the Hitchins equations, this is the so-called Hitchins spectral curve construction. Essentially, the point is that when I have a sequence of solutions to my gauge-theoretic equations which escape from the moduli space, what happens is that my section of the normal bundle, tensor some space of matrices, will degenerate to a solution of this equation. And simply what this equation tells you is that you will have locally two matrices which commute and which are normal. And two such matrices can be simultaneously diagonalized. So then when you take the eigenvalues of such matrices, that will essentially give you a two-valued section of the normal bundle. So that was very fast. So I apologize for that. But essentially, the upshot is that these equations are designed in such a way that the number of solutions should change when I have a section, a multi-valued section of the normal bundle. So that leads to some conjecture that maybe we can define this symplectic Thomas invariant by counting embedded curves with weights which count solutions to such gauge-theoretic equations. And then, of course, the main problem is to prove that this is well defined and that this number of solutions to the gauge-theoretic equation jumps in the way we want. So I think I have one more slide, but let me stop here. So thank you for your attention.
Great, let's thank Alexander for the great talk. Are there any questions for the speaker?
I wanted to ask about this last conjecture, the statement that maybe this gauge-theoretic count is the same as Thomas.
Mm-hmm.
Is there some strategy for why this might be true? I mean, other than the fact that, other than maybe try to establish that they're related to Gromov-Witten theory in the same way. I mean, but that would be a computational thing. But is there kind of a conceptual idea for why they might agree?
Yes. So. So the Thomas invariant also can be thought of as having like multiple order contributions. So the first order contribution of a curve is just the Euler characteristic of the symmetric product. That's the first. If you give me an embedded curve, say isolated in a Calabi-Yau manifold, then the PT contribution is the Euler characteristic of a symmetric product. And the symmetric product, you can think of it as the space of solutions to the Seiberg-Witten equations on the curve. So what I call the W1, the first order contribution, matches that. So you can ask, okay, so does the higher order contribution match the one from PT? And there is work of Diaconescu, which shows that, so these contributions on our side are given by counting some solutions to gauge-theoretic equations, but that you can always translate to the problem of counting certain sheaves on your Riemann surface. And then there's this work of Diaconescu, which shows that the sheaves you will be counting correspond precisely to the stable pairs counted in Thomas theory supported on that curve. So I guess what I'm saying that there is a local version, that the local contributions agree, but then of course the difficulty is how do you prove the global version of that.
I see. So the hope maybe is that there's just a decomposition in terms of the embedded curves, and then.
Yes. So if in some ideal world, if like let's say every Calabi-Yau manifold has all curves are rigid and embedded, then you could probably prove it simply by proving the local correspondence and comparing. But of course, the difficulty is that this is not the case. So there is some tension, right? Because in algebraic geometry, you just take the moduli space as it is, but in symplectic geometry, you want to perturb first to be generic. So then you have to understand what happens when you take that generic J and then move it to the non-generic one, and how does that affect the solutions to the vortex operation, the gauge theory.
Mm-hmm. I see. So like it'll be some strong invariance property of your proposed invariant, and then maybe you could run some degeneration scheme, like they do in algebraic geometry.
Yes. So you can also prove that symplectic definition of Gromov-Witten invariant is equal to algebraic definition, but I think this is going to be harder because then the proposed symplectic definition assumes that J is generic. So we don't have like Gromov-Witten invariance you can define symplectically even if J is non-generic, right? Here we fail at first step because if J is non-generic, you cannot talk about taking sums over embedded curves. So I actually think that proving that this is an invariant is going to be much easier than proving that it is equal to the algebraic. So this is two separate problems.
Okay, thank you.
I had a question at the start when you were talking about dealing with curves of all genus, and that
Yes.
is a reason why you look to currents to get a compactness result. I was wondering what's special about looking at the currents versus looking at the curves?
So I said that so there are many ways you can look at curves. You can look at them as like parameterize them and look at them as maps. You could look at them as subsets, and use. So the difference is in what topology you use. So if you are looking at them as maps, then you probably want to use Gromov topology. If you look at them as subsets, you want to use the topology maybe of Hausdorff distance, but that's a little bit too weak because then you forget about multiplicities. So currents are essentially subsets with multiplicities. So if you want to take limits of sequences of curves without prescribed genus, then you cannot look at them as maps because Gromov topology by definition is defined on the space of maps of given genus. So it doesn't tell you it doesn't give you any way of controlling curves whose genus goes to infinity, for example. Like the genus is built in Gromov-Witten theory, whereas it's not built in the subset topology or for example, current topology, because from the definition of a current, the genus doesn't even appear in the definition of the current topology.
That makes sense. Thanks.
Thank you.
Are there any more questions for the speaker? Okay, well, let's thank Aleksander again. Thank you so much.
Thank you for having me.